I want to leave our primes and prime arguments behind, and I actually want to talk about another proof idea. All of the proof methods we use, direct, indirect, contraposition, contradiction, they are all deductive proof. I want to talk instead about inductive proof. So first thing I need to ask is a vocabulary term. What the hell's the difference between these two words? What's it mean to think deductively? And what does it mean to think inductively? They must mean different things, otherwise they wouldn't have different terms for them. Deductive reasoning, deductive thinking, deductive proof. This is Sherlock Holmes, right? Sherlock Holmes considers himself a deductive reasoner. What's that mean?
Is it like because this?
That was our ideas of inference, right? But there's a little bit more to it when I think about deduction just versus general inference. Deductive ideas start with general principles about the way the universe works, and then we deduce specific things, right? Because of this, then this, then this, then this, right? But that becomes an overarching rule, gets distilled to specific examples. Which is why when we started with our deductive proofs, we started with all those rules of inferences. You can do if A, then B, if B, then C, so A implies C every time, right? That's a general principle, and then we used that sort of transitive idea. Inductive arguments are the reverse of those. I'm going to start with a bunch of examples and try and create a rule from them. So when I deduce, I start with the rules and I then look at my example. When I induct, I start with a bunch of examples and I try and create a general rule. So I'll start with a conjectured idea. Please do some addition for me. I want to look at the sum of consecutive, positive, odd integers. What happens when you add these totals? Add these sums up to give me totals?
Like 4 is 2 squared, 9 is 3 squared. 16 is 4 squared, 5 squared.
So now I have a conjecture. When I add up the first one number, I get 1 squared. When I add the first two numbers, I get 2 squared. 3 numbers gives me 3 squared. 4 numbers gives me 4 squared. 5 numbers gives me 5 squared. Aha! The sum of the first n odd positive integers is n squared. By the way, you should check. Does this work for the next one? If I add up the first 6 odd numbers, do I get 6 squared? Ah. As a matter of fact, I could do as many examples as you want. You add up the first 13 odd numbers, you're going to get 169, and that's 13 squared. Wonderful, marvelous. How do I prove this? Unfortunately, a direct proof fails. There isn't an obvious method to construct a direct proof. There isn't an obvious method to construct an indirect proof, or a contrapositive proof, or a proof by contradiction, or a proof by cases. Would have infinitely many cases in it, and that just sucks. So I want to try and prove this in a different method. The method of mathematical induction can be thought of in two different images for you. Either as a ladder or as a sequence of dominoes. I want to think about this. Which image do you like better, the ladder image or the dominoes image? I'll use either one. The ladder? Okay. If I want to show that you can climb a ladder, I need to show two things. I need to show you can get on the ladder at some point. And I need to show that if you're standing on one step, you can get to the next one. I want to start by showing a base case. I can get on the ladder. Getting on the ladder in this case means I want to be able to prove this for one particular value. Usually, I want to use the smallest such value. So that's step one. Step two is to show that if I'm already on the ladder, I can get to the next step. So I want to show that if I suppose my statement is true for some number, then I can do a deductive proof for the next number. So I'm going to call the value I suppose for k. And my goal is to show, using this, that I can show it's true for k plus 1. Do you see how it's stepping up the ladder? The first step, 1, shows I can get on the bottom of the ladder. I can get on the first step. The second step says if I'm on rung 1, I can climb to rung 2. If I'm on rung 2, I can climb to rung 3 and 4 and 5, and I can work my way up. If both of these are true, then my claim must be true for every integer from wherever I started on forever. I've said that, and let me actually, wait a minute. I think I need to quick copy that. If my lowest value happens to not be 1, maybe my lowest value is 2 or 7 or something like that, then it's true from there on. Page 336 has a picture. There's my ladder, right? I can reach the first step. That's my base case. Then my inductive case, from each step, I can get to the next one. If I'm at K, I can reach K plus 1. Since I could get on somewhere, that means I can reach any step I want. It just takes a while. We've done this idea before. We talked about recursive sequences and recurrence relations. I want to know what's happening in number 15. You're looking at 14 and 13 and 12, 11, and 12. Oh, I get to 1, and then I go bing, 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 all the way back up, right? If I think about this as a set of dominoes, what I'm saying is I can knock down the first one, and then each domino will knock down the next one. So, this means I need to write my claim in terms of a value. So, if we go back and look at the phrase I wrote down for the claim I wanted to show, I wrote down the sum of the first n odd positive integers is n squared. I'm going to make that a propositional function. P of n. This is the thing I am going to prove. I'm going to prove it by induction. Induction always starts the same way. Here's my sentence, my claim, in terms of some variable that goes over the integers. Now I pick the smallest possible integer that will work in there. In this case, that's 1. And I show that is my base case. The sum of the first n positive odd integers I don't even know how to write that. Let's leave that alone. Sum of the first 1 positive odd integer. That's 1. Plus nothing, right? Isn't that also equal to 1 squared? I have now shown my property is true for the value 1. I'm even going to write it that way. Square bracket, P of 1 is true. It doesn't have to be 1. It could be 2, 3, 7. It doesn't matter. It just needs to be some number. And then we go from there on. Questions about the base case? Okay. Now I got to do the second part, right? My induction step. How did the induction step read? I want to suppose my claim is true at some value. I'm going to write that down right at the beginning here. suppose P of K is true. Let me put that in words, so I've written it the same way before. The sum of the first K positive odd integers equals K squared. The sentence that I have just written down has the word suppose in front of it, right? That makes it a hypothesis. I'm even going to call it the induction hypothesis. A lot of textbooks tend to abbreviate that as IH. What is my thing I want to prove in the induction step? Starting from here, where do I want to go?
The next odd value of 3.
The next value of K, which in our case would be 2. But rather than do it for a specific example, I'm going to do it in the general case. So now I need to write down where I'm going. This is me being pedantic. You don't actually have to do this step, which is why I'm going to bracket it off again. I want to show P of K plus 1 is true using P of K. Oh boy. Think about this sentence we've written down right here. That's for P of K. If I go to K plus 1, that means I need to change that from K to K plus 1. And instead of looking at K odd integers, I'm looking at K plus 1 odd integers, right? So, all right, wait a minute. Let me write this down. 1 plus 3 plus 5 plus ... plus. Wait a minute. First, second, third, right? 5 is 2 times 3 minus 1. 3 is 2 times 2 minus 1. My odd numbers are 2K minus 1 rather than plus 1 like we've written them before. That makes that the kth odd number, right? So my induction hypothesis says that that adds up to K squared. That's another way to write my induction hypothesis. Instead of in words, I can write it as a formula. Like that, like having a formula. Now let's look at the next one. The next one would be the sum of the first K plus 1 odd integers. That would go 1 plus 3 plus 5 plus ... plus this one plus one more. What's the next odd integer in line? Because I have to add 2 more numbers, right? I have to skip one at, aha. Another way I could think of it is I could think of it as 2K plus 1 minus 1, right? That would be the next value. But if we multiply that out, don't we get this? Okay. I want to know, I hope that when all is said and done, I get a square. So what can I do to simplify this? I'm allowed to use my induction hypothesis. If I put a big set of parentheses here, isn't that the left side of my induction hypothesis? So I can replace that with a k squared. Here it is, I made it explicit. I used the induction hypothesis right here. That expression I just wrote down. Factors. What is it? Hey, wait a second. The sum of the first k plus 1 positive odd integers is k plus 1 squared. Isn't that what I wanted to show? I showed I could get on the first rung. I showed it was true for 1. And now, no matter what number you know it is true for, you know it's true for the next number. So it's true for the next one after that, and after that, and after that, and after that. And that means it's true for all of them from 1 to infinity. Now, there is one downside to the methods of mathematical induction. I need to have a pattern in the first place. Without that pattern, I have a problem. And if I don't have a clue about the pattern, I'm sunk. So most of the time, these proofs get created because somebody sees the pattern and says, hey, can I use this pattern in itself? In the same way that our recursion ideas said, I want to use this, let's call it again on a simpler and a simpler and a simpler. We're basically doing recursion kind of in reverse. Questions? There are hundreds of different examples that come from this. Here's a pattern. What do you get for these values? Right? All of those numbers are divisible by 3. I claim that works all the time. No matter what number you pick. Grab your calculator. 187 cubed. I have no idea what 187 cubed is. But you can calculate that, right? Subtract 187. Divide by 3. Your remainder 0, isn't it? Pick any number you want. Cube it. Subtract the original. You get something that's evenly divisible by 3. I don't care how big the number is. I don't know how to prove this. I don't know a direct proof for this. I'm sure we could write one if we thought about it long and hard enough and did some other tricks from other places. Screw it, let's do this by induction. Okay, I need my property P of n. P of n, my propositional function, is exactly what we've written up here. 3 divides into n cubed minus n evenly. My base case is when n equals 1. And I proved that right here, didn't I? So really the important part of this is the induction part of this. Every induction case starts the same way, with an induction hypothesis. What am I supposing? Careful. My conclusion is going to be about P of n. I want to suppose it's true for some other particular value. That's why I switched from n to k in the other problem. You can use any letter you want, but since I've used n in the general statement up there, I don't want to use n again. For some value k bigger than 1. And again, this is P of k being true. What do I want to show? That is true for the next one. 3 divides evenly into k plus 1 cubed minus k plus 1. Now, I haven't actually shown this yet. This is my goal. And somewhere in there, I'm going to use my induction hypothesis, right? So I need somewhere to show that this thing is divisible by 3. K plus 1 cubed minus parentheses k plus 1. Well, let's start messing with this and see what we get. Multiply this sucker out. When I multiply out k plus 1 cubed, I get k cubed plus 3k squared plus 3k plus 1. Now you'll notice what I didn't do. I didn't gather my like terms. I did that on purpose. By the way, if you don't remember this one, we did this with Pascal's triangle when we did a plus h, when we did derivatives back in Calc 1. It's been a while, man. Okay. I see some things that already have 3's in them. Let's set those aside for the moment. What's left if I set those aside? Because they're definitely divisible by 3, aren't they? I don't have to worry about those. Those have 3's in them. But if I take those two out, well, I've got a plus 1 and a minus 1. What's going to happen to those? And then what else is left? Careful. K cubed and k. And notice that the k cubed is positive, but the k is negative. Yes? Something just hit me upside the head. This. Where have I seen that somewhere? By my induction hypothesis, k cubed minus k must be equal to 3 something for m, an integer. That's what it means to be divisible by k, yes? So k plus 1 cubed minus k plus 1 is now 3k squared plus 3k plus 3m. And lo and behold, that is 3 times some integer, because k was an integer, and m is an integer, and therefore k squared is an integer, and when you add integers, you stay in integers. And that means 3 does divide k plus 1 cubed minus k plus 1. Which means I have shown the next thing is true. So now I need to write that conclusion again. The conclusion, by the principle of mathematical induction, I know 3 divides n cubed minus n for all n in the natural numbers. Because I started at 1 and I keep going up. Whew. Questions? I like induction proofs because they all follow exactly the same formula. Show your base step, then do your inductive argument. The problem I have with induction proof is figuring out what the hell to prove in the first place. Because it doesn't tell me why this theorem might be of any truth. It just shows, hey, this is going to work because of the way integers work. And that's really the root of a proof by induction. A proof by induction is based on the fact that the integers are in order. There's actually a foundational axiom. Remember we talked about the axiom of choosing, our ability to choose in diagonal argument? That's an axiom. It's something that is either accepted as part of the way you design the numbers or not. The ordering of the integers is an axiom. And that's just defined by the way we define algebra and the way we define numbers, and that's not helpful and insightful. It works, but I don't know why anybody would give a shit. So a lot of these inductive arguments don't look like they have meaning until I put them in another context. This is an infinite sum. We talked about sums in chapter 2, section 4, but we dealt with finite sums. Here is an infinite sum. This is something for calculus. By the way, if you are going to take Calc 2, this is where we'll talk about it in chapter 10, 11, in Calc 2. This is one of my favorite infinite series. If I take 1 plus a half plus a third plus a fourth plus a fifth, and I keep going forever, this goes off to infinity. This sum does not add up to a finite value. In calculus speak, we say that this sum diverges to infinity. On the other hand, start with 1, add a half, a quarter, an eighth, a 16th. the 32nd, the 64th, the 128th, keep going like that in powers of 2. I can write this as an infinite sum as well. Because this is 1/2 to the 0th power, 1/2 to the 1st power, 1/2 to the 2nd power, 1/2 to the 3rd power, 1/2 to the 4th power. That's 2. The fact that some of you are looking at that and going, uh-huh, and some of you are looking at that and going, what the is absolute music to my eyeballs. Thank you. How do I show that this adds up and this one doesn't? Let's ignore the 1 for the moment. Let's just look at this part, okay? Here is a square. It is 1 unit by 1 unit. Yes? Cut it in half. Just draw a line down the middle and shade in one side. What is the area of the shaded side? If I cut it exactly in half, what is the area of the shaded side? It's a half. Right? Now I cut this piece in half. What's the area of that? Repeat. 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 Am I ever going to get a number that's shaded in that's bigger than the total area of this square? So the number, no matter how much I keep adding, the number I'm going to add up to is less than 1. But the little tiny upper right corner that's unshaded, what's going to happen to it? It's going to get smaller and 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 smaller. The limit, as I go off to infinity, of that little bitty upper right corner, that area's limit is 0. So when I add up all of these numbers, I get 1. And then I added another one, so I get 2. Ta-da! I can hold infinity in the palm of my hand, people. I love math. But this adds up to 2. This blows up to infinity? Why the hell does this blow up to infinity? I'm going to do this by looking at pieces. What I have written down here is called a partial sum. Because the original sum went off to infinity, this is part of it. Yes? By the way, the reason we call these H's is because this particular series is known as the harmonic series. Because if you take a string that is 1 unit long and you pluck it and you pinch it at 1/2, you get an octave. If you pinch it at 1/3, you get a major third. If you pinch it at 1/4, you get to double octaves. If you pinch it at 1/5, you get a major fifth. The ratio of the music is based on the fractions 1 over whatever. So this is actually goes all the way back to Greek times, the harmony of the natural numbers. This is why music was considered a mathematical liberal art. Okay. I'm going to pick J to be a power of 2. I claim that H2 to the K is bigger than or equal to 1 plus K over 2. This is an induction argument. Here's my base case. When K is 1, then I'm doing 2 to the first, right? That's the first 2 numbers. Well, that's equal to 1 plus 1 over 2. So that works. Let's look at the next one in the pattern. Before I actually do the inductive proof, let me write out the pattern, see if it works. What happens when K is 2? I get 1 plus 1/2 plus 1/3 plus 1/4. Hey, wait a minute. A third is bigger than a fourth, isn't it? So this is bigger than 1 plus 1/2 plus 1/4 plus 1/4, isn't it? What's this add up to?
1/2.
And then I have another half here, don't I? So this is 1 plus 2/2. If K is 3, I'm doing 2 to the third. That's 8 numbers. 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6, 1/7, and 1/8. Oh boy. Okay, wait a second. We already know what this adds up to. Well, no, but we know it's bigger than 1 plus 1/2 plus 1/4 plus 1/4. Now for these, a fifth is bigger than an eighth, and a sixth is bigger than an eighth, and a seventh is bigger than an eighth. So I'm going to replace all of those by eighths. This adds up to a half. What's this add up to? So I have 3 halves, don't I? I see a pattern here. And I claim that based off of this ideal pattern, I should be able to prove this by induction. So the first 8 terms are bigger than 2.5. The first 16 terms are bigger than 3. The first 32 terms are bigger than 3.5. No matter how far I go, it's bigger than some number, isn't it? That means it's kind of go further and further and further. This goes kaboom to infinity. All of a sudden, I have an amazing proof in calculus about a series that diverges versus a series that converges. And studying about infinity is what calculus is based off of. Now, there is another version of induction where we actually use a stronger assumption. Instead of just showing that it's true for the one to get to the next one, I assume it's true for all the ones that came before. A question for you to think of in an inductive idea. If I give you a Hershey bar, and I ask you to break it into those individual little rectangles, how many breaks does it take? Now imagine a grid as big as you want. How many breaks does it take to break that grid into individual squares? That's an inductive argument, but it's not a simple induction. It's what's called a strong induction. We're not going to cover strong induction in any detail here. I just wanted to alert you to the fact that sometimes there's another version with a different hypothesis. I believe this is the last method of proof we are covering in this course. There are a couple of problems here that are going to take some work. We'll see you all on Wednesday. Have a wonderful rest of your day.